You know, we often think of AI as this one massive, super complex brain. But what if that's not the only way? What if we could build something just as smart, maybe even smarter, from a whole bunch of really simple parts all working together? Well, that's exactly what we're diving into today. We're going to unpack the APS architecture. It's basically a blueprint for building a distributed collective intelligence, a kind of swarm brain. So this really is the million-dollar question, right? How in the world can a group of simple agents with no one in charge, no central commander telling them what to do, somehow create a collective intelligence? How does order just emerge from chaos? It seems kind of magical, but the APS framework actually gives us a solid, mathematically grounded answer to this puzzle. And that answer is what's called a distributed cognition system. It's a fancy term, but the idea is simple. It's a system where the smarts, the intelligence, doesn't come from some central control unit. Instead, it bubbles up from all the tiny local interactions between these individual information entities. The APS, which stands for Agent-Based Predictive System, is the formal blueprint for making this happen. The intelligence is the network. Okay, so here's how we're going to tackle this. We'll start super small, looking at just one agent. Then we'll see how they connect with each other. And finally, we'll zoom way out to see the really cool stuff that emerges from the whole system, things like collective memory, and even a form of attention. It's going to be a fun ride. All right, section 1, a distributed brain. So any big, complex system has to start with its basic building blocks, right? And the real genius of the APS architecture is that it gets super precise about this. It gives us a solid mathematical definition for the simplest piece of this distributed brain, what it calls an information entity. So let's crack one of these entities open and see what's inside. It's actually made up of 5 key parts. First, you've got its representation. That's just what the entity is currently thinking about or representing. Then there's its internal state, which is kind of like its current mood or mode. Is it active? Is it confident? Next up, parameters. These are the knobs and dials it can tune as it learns. And of course, it has a memory, a little trace of its past to keep it stable. And finally, and this is super important, it has metadata. We're talking stuff like timestamps and where the information came from. This 5-part structure is the key, because it's what makes the whole system traceable and auditable down the line. Okay, section 2. Let's zoom in on just one of those 5 pieces, an entity's memory. This is so crucial because think about it. If an agent just reacted wildly to every single new bit of information, the whole system would be pure chaos. It needs a way to remember its own history to stay stable and have some context. And this is where things get really cool. You have to understand the difference between 2 of those components we just saw. The internal state, that S, is the fast-moving part. It's reactive. It's the entity's current vibe. But the memory, that M, is the exact opposite. It's slow changing. It's an aggregation of the past. You can almost think of it like a heavy flywheel on an engine. It provides momentum and stability, and it stops the entity from getting jerked around by every little bit of noise. Okay, I know, an equation, but don't panic, it's actually way simpler than it looks. All this thing is saying is that the memory tomorrow is going to be mostly what the memory is today, plus just a tiny little piece of what's happening right now. The classic name for this is an exponential moving average, or even better, a leaky integrator. Imagine a bucket you're filling, but it has a tiny little hole in the bottom. Old water is always slowly leaking out. This is brilliant. It means old, irrelevant information just naturally fades away, keeping the entity focused on the more recent past. Okay, so now we have these individual agents, each with their own stable memory. They're like little islands. But how do we build a continent? How do they start talking to each other and forming a network? The whole magic lies in this one little thing called the synergy signal. Think of synergy as the handshake between 2 entities. It's just a single number, a score, that 2 entities calculate to see how well they get along. A high score can mean a lot of things. It could mean, hey, we represent really similar ideas. Or maybe you have a puzzle piece that fits perfectly with mine. Or even just, when we work together, we both do a better job. This simple local handshake is the absolute engine of self-organization for the entire network. It's everything. All right, so we've got individual memory down. But what happens when you have thousands or millions of these agents all calculating synergy with each other? This is where we zoom back out and see how the entire network develops its own memory. And trust me, this is where it starts to feel like magic. Now, this is a huge mental shift. You have to get this. Collective memory isn't like a file stored on a hard drive. It's not in any one place. The memory is the pattern of connections. It is the structure of the network. When a stable, persistent pattern of strong connections forms between a group of entities, that is the memory. It's a completely different way of thinking about where information lives. So let's just put them side by side to make it crystal clear. Individual memory is stored inside an entity. It's that leaky bucket, that running average of its own past. But collective memory, that's stored between entities. It's an emergent property of the whole group. It's that stable pattern, that web of strong relationships. And this abstract idea of a stable pattern actually has a concrete name in the APS framework. It's called a persistent cluster. And it's exactly what it sounds like. It's a clump of entities that are all just really, really into each other. They have high synergy scores internally, but they're not really connecting with anyone on the outside. This stable little island of high connectivity, that is the physical manifestation of a memory. It's a piece of knowledge that the network has learned and decided to hold on to. Okay, great. So the network can form these stable memories, these persistent clusters. That's how it stores long-term knowledge. But what about the here and now? How does the network decide what's important right now and focus its resources on it? Well, for that, you need a different emergent property, distributed attention. And just like with memory, there's no central boss here. It's not like there's a guy in a control room pointing a spotlight around the network saying, okay, focus on this now. No way. Instead, attention emerges from a simple constraint. Every entity has a finite relational budget. It only has so much connection strength it can hand out, and it's constantly dynamically reallocating that budget to the connections that have the highest synergy at this very moment. And this all happens in a really elegant, continuous loop. It's a three-step dance. Step 1, every pair of entities calculates its local synergy score. How well do we work together right now? Step 2, based on that score, they nudge their connection weights. If synergy is high, the connection gets a little stronger. If it's low, it gets a little weaker. And the crucial step 3, the whole system gets renormalized. Everybody's connection strengths are adjusted to make sure no one is spending more than their attention budget. It's this constant system-wide optimization that lets the network's focus just flow, shifting organically from one important thing to the next. So, okay, we've gone pretty deep here. We've seen how these incredibly complex behaviors like memory and attention can just emerge from these simple local rules. But you might be wondering, why go to all this trouble? Why be so formal and mathematical about everything? What's the big payoff at the end of the day? And here it is. This is the whole point. Because everything is built on this solid mathematical foundation, the system doesn't just work, it comes with guarantees. You get stability right out of the box. You have mathematical proofs that the system won't just explode into chaos. You get auditability. Remember that metadata? It means you can trace back why the system did what it did. You get robustness, thanks to those memory buffers. And maybe the most important thing of all, you get controllability. This is the opposite of a black box AI where we just cross our fingers and hope it works. This is a system that's designed from the ground up to be transparent and understood. And really, that leaves us with a huge question for the future of AI. What's going to be more important? Are we going to keep chasing raw performance at all costs, building bigger and bigger black boxes that we don't fully understand? Or are we going to shift our focus to architectures like APS, which are maybe just as powerful, but are also provably transparent, auditable, and stable by their very design? It's a massive debate, and it's one that's shaping the next AI revolution. Something to think about. Thanks for joining.